Thank you for joining us for today's webinar on adding physics to glTF. Our presenter today is Eoin McLoughlin from Microsoft. First, a couple of housekeeping items. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar and we'll share the link along with the slides later this week. At the end of the session, please complete the short survey form to help us better design future events. With that, I'll hand it over to Eoin McLoughlin, Principal Software Engineer at Microsoft. Eoin?
Thanks, Jeff. Let me share my screen. Fingers crossed this works. Okay, so today I want to talk about how to add physics to your glTF assets, the work we've been doing in this area. So here's a rough agenda for the day. I'm going to talk about why you might want physics in glTF, what kind of physics we're doing, because physics, I'm using this is quite a broad term, but I actually have quite a narrow definition. And then we'll go into the specifics of the design of the extensions that we need, rationale and justification for the different features, with some examples of how you might use them, and some demos of the JSON that's involved. And then we'll talk through what the timelines are and where we are with the current state of the extensions. So let's get started. Why might you want to use physics? So one of the things physics does is it makes procedural animation, you get it for free. A scene like you can see here is not really feasible for an animator to animate, at least in a normal amount of time. By using a physics simulation, you get much more believable results for less file size, because you don't have to bake this data into the animation. And the scene is more realistic, and users can interact with it in ways that they wouldn't be able to do with an animation. It makes it a lot more fun. I've personally spent hours looking at this particular scene, just watching the marbles roll around. But even if you're not using simulation, physics gives you some capabilities that you probably wouldn't otherwise get. Physics engines typically are concerned with collision detection. It's a large part of what they do, and they have exposed certain algorithms and geometries in a way that makes collision detection really fast. And a physics engine will typically expose these queries. They'll allow users to use the collision detection algorithms in ways that might be beneficial for scene understanding. For example, you might do raycasts, which would be useful for visibility queries, to see if there's a straight line from one region to another, without having to go onto your GPU and simulate that there with maybe a large overhead time for the dispatch. Another really useful query does that you wouldn't otherwise get with render geometry is the closest point between two objects, which, like, how far can I move these objects before they collide? What's the closest point between them? You can use that for all sorts of visual UI feedback, like where is the player's hand or the user's hand? What objects are they close to, for example? What objects might they be able to pick up? And in this illustration here, we've got something that we call a shapecast, which is given an object, try and move it in a particular direction before it hits something, and figure out how far can an object move before it will collide with something else. And this kind of shapecast query is really useful for positioning objects, as you can imagine. It avoids the artifact where you might see floating geometry. It's because you're using the physical geometry of the mesh. It's much more accurate than, say, a bounding box representation might be. And you can build all sorts of interesting things on top of that, like room planners, object position tools, character controllers, for example, might use it to try and move a player around a scene. So even though you might not be actually simulating anything, the algorithms that physics provides and the tools physics provides are still really useful. So I've been using physics quite broadly. So I'd like to kind of narrow down on what we mean by physics. So right now we've just been focused on what we call rigid bodies, or what the industry calls rigid bodies, which is objects that don't change shape. And the rationale for that is that technology for rigid bodies has been around a long time. There's a lot of different simulators out there, maybe not as much as I'd like for any budding physics programmers in the audience. But the rough concepts and the ideas, the words, jargon they use, there's a very broad overlap. So it's ripe for being standardized. Now, lots of different engines, lots of different simulators will have functionality that maybe only that engine has. We haven't really concerned ourselves with that. We're only looking at the kind of shared core functionality that's common to all the different physics engines out there. Rigid bodies are generally, the engines are generally suitable for real-time simulation as well. Whereas someday we would like to tackle deformable objects, but that's a lot harder. There's a lot of different ways to do that. Lots depending on the simulator and the solver in use by the simulator. They might have different representations of the same objects. They might want to express the simulation and the geometries in different ways. So there's a lot less agreement in terms of what engines are out there and what techniques they use, unfortunately, for deformables. So it's going to be a lot harder to do that, just purely because there's less standardization in that domain. So right now we're just focused on rigid bodies because that's tractable. So one of the first things we're going to want to do is define a collision shape. Obviously, you can't collide two objects together unless you know what geometry they are. And while you might be tempted to use the render mesh for that, it's not really what physics engines do. So I'm going to keep using the word physics as shorthand for rigid body simulators. Just that's out of habit partly, and it's also easier to say. But rigid body simulators tend to prefer convex shapes. There's a couple of reasons for this. One is just the time complexity. Like this chair might be made of thousands of triangles, and if you want to collide those together, two chairs together in real time, you're looking at tens of thousands, hundreds of thousands of triangle intersections. And that's not really viable for real time. But more so than that, there's a behavioral issue. If the triangle mesh, the triangle soup doesn't necessarily have a defined inside and outside. So if you were to overlap two chairs on top of each other, the physics engine would have a hard time pushing them out because it wouldn't be able to tell which part of the chair was inside, which was outside. So it would have trouble separating them. Whereas with convex shapes, a convex shape has to be a closed geometry, has to be manifold. It has a defined inside and outside. So the physics engine has a much easier time with it, with a convex shape. And a single convex shape can approximate many, many triangles. So here we've decomposed with an automated tool. We turned this chair into maybe 50 convex holes. And we used a tool to do this with a slider to say what's my trade-off for accuracy versus number of convex pieces I get. And depending on the level of kind of users interaction you get and the amount of performance and the amount of fidelity you want, you could change your slider to be more or less accurate and trade off the number of holes for the accuracy. So this is the kind of data that physics really wants to work with, is rather than seeing a triangle soup, see a set of convex objects or a single convex object. So what we've done is we've made this KHR collision geometry extension to provide a set of convex shapes. This isn't necessarily a physics-focused extension. The hope is that future extensions would also be able to use this. So there's no physics-specific information in there. These are the sets of shapes that it exposes. So a sphere, a capsule, cylinders and cones, boxes, a convex hull, which is the convex object that wraps a mesh, and a triangle soup, which could be concave, because despite my disparaging of the triangulated mesh, they're still useful, particularly for static geometry, objects that don't move. They're very heavily used. Now, this might seem like an arbitrary set of shapes, and it is to some degree. With the exception of the triangle mesh, they have the property that they're all convex. So there's lots of good algorithms out there. Physics engines understand them and can deal with these really quickly. The hope is they'll be useful for any extension that wants to do some degree of collision detection. So imagine a 3D UI, for example, might use boxes or cylinders to build buttons and dials. So there's hopefully some degree of flexibility in there. The shapes by themselves, they don't do anything. They look like this. They're a child of root glTF object, so they live at the document level, and they just have the bare set of properties that you might expect from those. So notably, things like the sphere you can describe with a single radius. You don't need to make a mesh that's in the shape of a sphere. That's obviously good for your memory usage, in terms of the file size. It also means you don't have to calculate what radius the sphere would have when you load. They're just the minimal descriptions of these objects. The capsules and cones have different radii on the top and bottom, which allows some flexibility in terms of what geometry they might expose. You might make a cylinder or a capsule with the two radii being equal, or a cone segment, or a tapered capsule if they're different. So these objects, because they're at the document level, they don't do anything by themselves. They're just the descriptions of pieces of geometry. So we need to be able to use them. So in the next step, we've got the KHR rigid bodies extension, which is right now the only consumer of the collision geometry extension. And one of the things the KHR rigid bodies wants is to define what the shape of an object for collision detection might be. And this doesn't necessarily have to match the rendered geometry. Again, like as we saw with the chair, physics probably wants to take an approximation of the rendered geometry. So here we have a node. It's just a normal node. Now it has a render mesh. It can have children. And in the extensions object, we've added a collider. And that collider has a shape property, and that indexes into the array we saw earlier, the array of collision geometries. This means they can be shared. You might have lots of instances, lots of different nodes referencing the same shape. And what we've got in KHO rigid bodies is just a collider by itself like this. That's just a static piece of geometry. There might be a static body in an engine. It might be a shape in another. Depends on the implementation, obviously. But what we're saying is this object doesn't move. And it might have children. It might have more child shapes underneath it with more colliders. And that defines whatever the set of that object is in terms of its physics collision geometry. But a static object, that's fine. It's not that interesting. I mean, it's obviously important, but what you really want to do is see things moving. So the next object that we've added via the KHO rigid bodies extension is a motion. And that says this is a node that can be moved by the physics simulation. And it motion for physics for rigid bodies, you need certain sets of properties. You might need a mass, which tells you how heavy something is. The inertia tensor and center of mass will tell you where that mass is distributed. Velocities will tell you like how fast it's moving, and kinematic and dynamic switches allow you to say whether you want the object to be really physically under physical simulation control, or you want it to be animated but still have an effect on other rigid bodies, which is a common technique for the critical pieces of critical objects that need to get to a particular place, but you want to be able to push other objects out of the way. The other thing we've added is gravity factor, which is not a physically realistic property, but it's extremely useful, which just allows you to scale the amount of gravity. So in this video, which I'll play, we have several examples of objects using maybe exaggerated versions of these. This little toy here has a center of mass that's quite low to its base, simulating what the actual toy would do, where they've added extra weight down the bottom. That allows it to always roll itself upright. This purple box has an inertia tensor with infinite mass, so it's impossible to rotate, and that means it always stays oriented the same direction. This wheel has infinite mass and no gravity, but a finite inertia tensor, so he can turn but not move. And these balloons have a negative gravity factor. So if we were to play these, we get all these nice little effects that you get by tweaking these properties. And again, these are not physically realistic necessarily to say this object has an infinite inertia tensor. I don't think you can make one of these in real life, but it's useful for some interactive use cases, particularly like characters. You might want a character to stay upright indefinitely, regardless of what he's interacting with. So what does that look like? Again, we have a normal node. He might have a render mesh. Again, he might have children. And we've got in our rigid bodies extension, we have the motion object. And all of these properties, this isn't the whole set of them, but gives you the right idea. All these properties are saying, okay, this is how heavy this object is. This is how fast it's moving around. This is where its center of mass is. With the expectation that most of the time, for example, here we haven't specified an inertia tensor. Most of the time, an artist does not want to type in an inertia tensor, while artists might have a rough idea of how heavy an object is. The distribution of mass around the object in tensor form, I think, is generally beyond everyone. So physics engines will typically have a method to calculate this automatically if it's not provided, or usually what people do is they will use a tool to calculate it, and then might scale it to achieve whatever effect that they want. If you want to make an object hollow, you would scale up the inertia tensor, for example. So there's some expectation that these properties are optional, with the intention that the physics system the simulation would be able to calculate appropriate values that might depend on the shape, how big it is, like what you've decided it's made of, how dense that object is. So aside from the motion, we can see this object also has a collider. He has a shape. Again, that's indexing into the earlier collision geometry nodes we saw. And again, it can be shared, it can be used by multiple different nodes. But a new property that we didn't mention before was a material. So for all its niceties, the PBR materials that are in glTF don't tell us how an object physically behaves. It'll tell us how it looks, but not how it behaves. So we need a physics material. So again, there's some divergence here in how exactly real life works and simulators work, but we've decided on a simple physics material model that just includes friction and restitution. That allows you to do things like on the left, we might have a bar of soap that might be slippy and has a low friction, while the honey has a much higher friction, slides down the slope a lot. That's a lot slower. And on the right, we have basketballs and bowling balls. Basketballs generally bouncier. And this is a property that can be provided per collider to say, okay, this is what the object is made of physically. And obviously that's independent from its render geometry. And again, those physics materials are child of root objects. So they live at the document level. I didn't have enough room to put in a sample here, unfortunately. But they live at the document level, so they can be shared. You can make your material for rubber, you can make your material for honey, etc. Now, it's not exactly the way real life works. We've got a simple way of describing how to combine those materials, like what happens when you put rubber on ice, or how do the friction values combine? What's the resulting friction when those two materials meet? In real life, it actually depends on the combination of the materials. Like there's no mathematical formula that will give you the combination, unfortunately. So to some extent, what we've described is an approximation, but in our experience writing physics engine, this seems to work well enough for at least sort of interactive use cases, maybe not people making serious simulators where accuracy is critical. But this can be extended. You might want to add a pairwise combination, for example, which would much more closely model how the real world works. And that's enough to give us simple objects to describe how lots of the objects that you might interact with today behave. But another useful thing that we need is the ability to join two objects together. So we call these joints. And again, this is a child of root object, which we'll see later. And it allows you to say, these two objects need to be connected to each other, and they have certain degrees of freedom. And a degree of freedom is like how those objects can move relative to each other. So for a hinge, for example, like at the point of contact, those aren't allowed to move any further away than they are, but they're allowed to rotate around kind of the location of the hinge. So there's lots of different constraints or joints that you could build in real life. Hinges, drawers, shoulder joints, knees, which is a kind of hinge, I suppose. And what we've got is a very generic way to describe the limits, whether they're one-dimensional, two-dimensional, or three-dimensional, and a way of composing those together to build the complete set of joints. And that allows you to say, build a door that can only open a certain amount, or build a drawer that can slide open a certain distance. And those limits can be soft, optionally. They can have springs. So again, you might imagine that your drawer has a spring trying to close it, and gives you a nice behavior of something that has some compliance. And the other thing that we're currently working on for the joints is a drive. So that's an object which would apply forces within the constraint space, within the joint space. And it's a nice way of bridging animation and simulation. You might consider that if you have an animation applied to an object that is physically simulated, you don't want to always move the object to where the animation should go, because that, or where the animation says you should go, because that might be physically unrealistic. So a really nice way of doing this is using drives associated with the joints. So rather than just opening a door and swinging it open, you might use a drive to apply the rotational force or the sliding door effect in your supermarket simulator, and that drive could have a max force associated with it. So if there was another object in the way blocking it, you'd get a physical response rather than the animation just saying this object should be here now. So that's a work in progress, and it's a nice way of bridging the gap between animation and simulation. So what a joint looks like, this is our kind of composition of those limits, and this describes something pretty close to what the video is displaying. So it says on our linear XYZ, we each chain can move 10 centimeters. On angular 0 and 2, we can rotate minus 1.1 and plus 1.1 radians around angular X. And on angular axis 2, or Z rather, we can't rotate at all. And the other one might be the rotation around Y is free, so that the chain can rotate freely in that around that axis. I don't think this is necessarily completely accurate to what's being displayed here. But you can, again, these are child of root objects. So if you have the same hinge on the same door, this can be referenced from a single node, so that you can reuse the same object again and again. And then the last thing we have, once you've combined all of those things together, what you'll find you need is collision filtering. So again, this is something that all those engines have, where generally you want a way to say these objects shouldn't collide, because if you've got these approximations for your render geometry and you've constrained a bunch of them together, you've added joints between them, you're going to have objects that overlap. And if they weren't composed of this approximate collision geometry, they wouldn't really overlap. But unfortunately, due to taking these approximations, you need a way to say, don't resolve these collisions because I know they're okay. For example, this ragdoll or this character here, his arms overlap his shoulder and his torso simultaneously. So we want to be able to say the physics system shouldn't collide those objects together, because if the collision system tries to push out the arms and the joints try to pull them back together, you're going to get some strange jitter, some fighting, something that will look unnatural. A lot of people also use filtering for optimization. For example, if you have a really large object, like a car or a truck, you might not want it to collide against the high resolution pieces of geometry in your scene. You might want it only to collide with the low resolution ones, so that you can't tell the difference between the truck colliding with a high resolution chess piece or a box that represents that chess piece. But there might be other scenarios where you do want to use the high resolution geometry for higher fidelity collisions. So a collision filter allows you to sort of LOD almost those objects together for depending on their pairwise interactions. And you can use it for application specific use cases. Here's in the JSON here, we've got some sort of object that might have importance for your application, for saying, okay, should my character be allowed to enter this region, or should it affect whether a character can see through those objects, if we're thinking about those raycasts we mentioned earlier. And this collision filter, every engine seems to have a slightly different implementation. Usually there's hooks to install custom filters, but there's no sort of uniform representation of what a collision filter looks like. So we've gone with quite a generic description of identify what arbitrary strings, names of systems or groups that the object is a member of, and what groups that object collides with. Typically those then get turned into bit fields in implementation, and you and the bits together, and if there are any ones left, the objects do collide. But the idea here is just to assign sort of application specific or asset specific strings to identify what utility an object has. So there's nothing, these important high-res visibility query character aren't defined in the spec. They're totally arbitrary user-defined labels for describing what their use case is. And when you pull all of that together, you're going to end up with something like this. So this scene, I think, uses all of the above functionality. If it plays, oops. It uses all of that functionality together in some way. And maybe as a physics programmer, my using the system badly hat, my senses tingling that I'm doing things I shouldn't really. But again, this is one of those really fun scenes that I enjoy looking at, and I've spent hours probably rerunning it. Yeah, so that's it come together in probably not a particularly useful scenario, but a fun one. And now let's see, we're kind of nearly feature complete in terms of what the spec offers. This is the short-term glTF roadmap, or it's an approximation of it. We're kind of hoping to get through the public comment period and get the physics really refined within the next quarter or so. So by the second quarter of 2024. This is approximations, of course, might change. I don't take any of this as gospel, please. And what do we have left to do in terms of physics? So as I mentioned, of the motors, want to get those finished up, and the documentation and samples around them. This is sort of the current preview asset that I'm working with, which needs a bunch more work, but this is the sneak preview. And we need to do a bit of work with the integration with the object model, which you might know as animation pointer. So that defines a couple of objects, or a JSON pointer to animate objects and say what things you might want to be able to change, what properties and fields might be mutable or immutable. And the KHR interactivity spec, which if you haven't seen the previous webinar, is excellent. Talks about how to add interactivity to glTF assets. So there's some expectation of functionality of synergy between those that we want to get typed up and formalized before I really consider the physics spec done. So the link to the draft extension here, it's on my personal GitHub at the moment. There's a desire to get that into the official repo once probably all these loose ends are tied up and all the little bits of documentation and decisions over naming are all resolved. But that's roughly my plan for finishing up the extension and for getting it to where it needs to be. And I think that's all I've got. It is.
Wonderful. Thank you, Eoin. I appreciate all your time and effort in putting this together. Next up, we have the Q&A portion of the webinar. If you have a question for Eoin, please use the Q&A button on the Zoom toolbar at the bottom of your screen. I'll start things off with a question for you. What sort of physics functionality might be available using the KHR interactivity extension?
So, okay, yeah, that's a good one. That's very much been on my mind. So the KHR interactivity, if you're not familiar with it, it describes sort of a node graph for doing calculations and performing modifications to nodes in the scene. And a lot of them might be done via directly changing the properties of an object. So you might try changing a node's translation, for example. But for physics, there's kind of additional functionality that you might like to expose. Like the collision queries would be a good candidate for saying, maybe I want to write an interactivity graph that positions an object such that it's on the floor inside this room, rather than just trying to change the translation directly. You might want to apply forces to objects that are dynamic, rather than changing their position. And there's lots of different ways you might apply forces. Just mathematically, you might try changing the linear velocity. You might try applying an impulse. You might try applying an impulse at a specific point on an object. So being able to apply impulses or apply forces on an object might make it behave more realistically, versus just changing the object's or the node's translation, for example. Because applying a force, you take into account its mass, so it'll roll or bounce around much more realistically. So thinking about what kind of nodes we can expose there that will make people's lives easier. And again, you want to minimize the amount of math you kind of have to do by hand, especially when you take into account things like inertia tensors.
Yeah. And then how does the KHR rigid bodies extension handle baking of physics data, which might be computational?
Okay, so yeah, okay. One of the things you might physics engine might do when we looked at the definition of the collision geometries, um, those just referenced meshes, for example, particularly in the case of the convex hull and the mesh shape, an individual engine probably wants to do more processing on those objects. So you might want to turn the triangulated mesh into a bounding volume hierarchy, for example, which will speed up the collision detection, which is a large part of what makes physics engines fast, is sort of building spatial trees. Um, so the extension doesn't go into any details on what you might do to sort of speed up that load time or minimize the amount of bounding volume hierarchy calculations or convex hull calculations you might want to do. Just there's not a huge amount of overlap between what the different engine implementations store. So what I'd anticipate is probably if asset loading or geometry processing at load time was problematic, different engines might want to add in a buffer that had sort of a pre-baked version of the representation of the scene, as a way to sort of avoid recalculating the mesh data or the engine specific mesh data every time.
And what is the expected interaction between glTF animations and physics?
Okay, so glTF files themselves can contain animations, and they can animate a couple of different things. Obviously, with the animation pointer, the object model stuff, this is there's some additional flexibility there, but the animations currently you can change the transform of nodes, and that can either just change the transform of nodes, or it can change the transform of nodes which represent bones in a skinned mesh. And when we talk about rigid bodies in this context, rigid bodies are usually not changing shape. But engines have some degree of being able to handle this automatically. So it probably depends on the use case and depends on like precisely what the artist is trying to achieve. You might want to, if you've got an animated mesh that has an animated skinned mesh that has a collider, you're probably going to have to recalculate that mesh every frame or update it every frame on CPU, maybe even rather than being able to just do your skinning purely in GPU. Similarly with nodes, if you change the transform of a node that maybe moves a shape relative to another shape, you might have to update some internal physics data in a way that's maybe not physically realistic or physically maps exactly onto what the simulation does. But I'd be hesitant to say it should be forbidden. I think if an artist is trying to achieve something in particular, they should the physics engine should be making a decent attempt at mapping that animation to something that maybe makes sense in the simulation.
Wonderful. Thank you, Eoin. Thank you for all the work you've done for glTF physics and putting this webinar together. We appreciate all your time and effort today.
Thanks.
And thank you all for joining us. As you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is important to us to help us improve these presentations. And please let us know if there are any other Chronos-related topics you may be interested in. Thank you for joining us. Have a great day.